My name is Rosimar Rios-Berrios, and I am a scientist at the NSF National Center for Atmospheric Research in Boulder, Colorado, in the United States, and I'll be one of the moderators of today's event. This webinar series is part of the WCRP Digital Earth's Lighthouse activity. The aim of this series is to help maintain a more regular and open dialogue between active researchers and users on the development and evaluation of kilometer-scale global and large domain models across the world. We plan to hold seminars every 2 months, spanning a range of groups working on kilometer-scale modeling around the world. You can find a previous recording of the previous events via our webinar page, which will be linked on the slides. The focus for today is on kilometer-scale modeling for destination Earth's digital twins and the work of Benoit Vanniere and colleagues at the European Center for Medium-Range Weather Forecasting, or ECMWF. Before we get started, I will pass it on to one of our other moderators today, Huw Lewis.
Hi, and hello to everybody. My name is Huw Lewis, and I work at the Met Office in the UK. And just before we introduce today's speaker, to give you an overview of how the session's going to run. So Benoit will give us his presentation, and at the end we'll have a time to work through some questions and answers. So during the talk, please feel free to post some questions in the Q&A feature in your Zoom window. And you can also use the thumbs up to upvote any questions you want us to reach earlier in the Q&A session. Please reserve the chat for any kind of technical issues, and we can try and address those through the talk. Hopefully the Q&A will help us to get a lot of interaction and a lot of feedback on what's being presented. So I'd encourage you to use those. We've already mentioned to Benoit we'll try and give him a warning if we're going too deep into that Q&A time. As you'll have seen, we're recording today's event, and we will share the link to that recording after the event, and I'd encourage you to share it with your colleagues and let them know about this webinar series and future events.
It is my turn now to introduce our speakers. So Benoit Vanniere is a researcher at the European Center for Medium-Range Weather Forecast, or ECMWF, where he coordinates the experiments and evaluation of the weather-induced extremes digital of destination Earth. He has made numerous contributions to the field of high-resolution climate modeling, and we're very excited to have him with us today, sharing some of that work. Prior to joining ECMWF, Benoit held research positions at the National Center for Atmospheric Sciences and at Imperial College in London, following completion of a PhD at the Institut Pierre-Simon Laplace in Paris. Today, he will share insights about kilometer-scale modeling at ECMWF for digital Earth's digital twin. Destination Earth's digital twins, my bad. With that, welcome, Benoit, and the floor is yours.
Thanks a lot, Rosie and you, for this introduction. Can you see my slides?
Yes, we can.
Yeah, looking good.
Excellent. Thanks a lot. So thanks for giving me the opportunity to speak today in this seminar series. I will present today the work that we are doing in Destiny on advancing Earth system models for the digital twins under the project Destination Earth. And I'm giving this presentation on behalf of all the teams involved in the project at ECMWF and in our partner organizations. Destiny is funded by the European Commission to develop new tools, but also to propose a new framework to address weather and climate impacts. And in that, it serves both the European Green Deal and the European digital transition. It is commissioned to 3 interested entities: ECMWF, ESA, and EUMETSAT. So 2023 was a great reminder to us all of the urgency of being equipped with new tools to address weather and climate impacts. The last 10 months have been the warmest ever recorded by ERA5, and they have all been 1.5 degrees warmer than the pre-industrial average. And at the same time, Copernicus tells us that Europe has experienced many extreme events, widespread and devastating floods like in Slovenia. We have experienced unrecorded areas, burnt areas and wildfires in the southern of Europe. And we have experienced unprecedented marine heat wave. All those extreme events total to 13 billion economic losses. So if we want to address those impacts, the current systems that we have are the climate projections provided by CENIP, together with a weather forecast produced by NWP centers. But those are fundamentally disconnected from impact sector models. And then further downstream, users sometimes have difficulty manipulating large volumes of data without the adequate tools or with limited bandwidth to retrieve the data. The Earth system models have limited resolution, meaning that they cannot always represent the scale at which impact occurs. Small-scale processes are missing, those which are conducive to extreme weather. And the experimental design is not always flexible, and the frequency at which the simulations are delivered does not always allow users to make decisions in time. For instance, CENIP is an exercise which is repeated only every 7 years. So if we want to make progress and if we want to go towards digital twins, we need to develop workflows that would integrate Earth system models together with impact sector models. Another essential feature is interactivity and allowing user applications to stream high-frequency data that will not be saved otherwise, but also allow institutional users to request specific simulations tailored for their needs. We are working on improving the quality of Earth system models, and that will be one of the main focus of my presentation, to bring them to the kilometer scale and also to improve the physics needed to simulate those scales. One of the major challenge for us is to address uncertainty. We will use physics-driven ensembles as traditionally done and scenarios, but we should also explore machine learning based solutions to address uncertainty. And finally, the need is also to bring this system to operation and to deliver weather impact sector predictions, but also to try and operationalize multi-decadal climate projections. So this is possible thanks to the advances, science advances on Earth system modeling, and in particular on global kilometer scale. NextGEM is a project which performs multi-decadal climate projections at kilometer scale 30 years into the future, so we can do that now. ERI is looking at the role of fine-scale ocean eddies in the climate system. And InSight is a project that has investigated what is the physics needed in the IFS and the assumptions in the dynamical core to simulate tropical cyclones all the way down to the resolution of 1 kilometer. And so you see now very nicely how the 10-meter wind is finely represented on the video on the left, engulfing in very narrow valleys. You see how sea ice cracks and leads can open in the Arctic sea ice, and those were not simulated before. They will not only allow to bring to users the information they need at the kilometer scale, but they will also allow to better represent the formation of extreme weather. And we can also hope that those kilometer scale processes have an upscale effect on the large-scale circulation and on the mean state of the atmosphere, bringing more accurate simulations. We are also relying on technological advances, and we will leverage the pre-exascale supercomputing facilities of EuroHPC. We have an access in Destiny to 3 of the 10 largest supercomputers in the world. And in particular, we want to exploit their GPU capabilities. We have worked on porting and adapting the IFS to a GPU. And we run now on the AMD GPU of Lumi, the various digital twins of destination Earth. We have been supported to get there by easy ways. We helped us improve the scalability of the IFS to run all the way to 1 kilometer, and also to improve the performance of the model by moving towards a single precision. So we are now in a position where we can run 5 kilometer global simulations with a throughput of 240 simulated days per day on 256 nodes. So the scientific and technological advances mean that we can now envision to build weather and climate digital twins together with EuroHPC. And there are 3 main features. First, for the first time, we will allow users, we will provide an institutional framework for users to request the simulation that they need. We'll bring kilometer scale information to simulate the scale at which impacts occur. And finally, we will exploit all the innovative AI developments, not only to simulate the Earth system and to address uncertainty, but also to enhance the interactivity with the digital twins and to extract information, for instance, by developing AI-based chatbots. Below, you have a little timeline of Destiny. In phase 1, we built the digital twins, we deployed them on EuroHPC, and we have tested them with a number of use cases. On the 10th of June, in 1 month, we will have the official launch of the project, where users will have an access to the various components of Destiny, the core service platform, the data lake, and the digital twins. And we will continue during the phase 2 until June 2026 to move towards a more operational Destiny system. So in this novel information system, ECMWF is building the first 2 digital twins for weather and climate together with 116 partner organizations, but also the digital twin engine, which is this collection of softwares which orchestrate the way the digital twin work. EUMETSAT is building the data lake, which is the archive, the rolling archive, which will host the data produced by the digital twins. And ESA is developing a core service platform where users will be able to visualize the outputs of the digital twins, retrieve data, but also request tailored simulations. In all of that, we are working in a co-design approach with users, and we already see how their input could influence the data portfolio of Destination Earth, but also the workflow that we design. And the digital twin engine, which is this collection of softwares which orchestrate the digital twin. So we have first EasyFlow, which will manage workflows in a distributed environment of EuroHPC from those various supercomputers. Loki is a software for code refactoring and GPU adaptation. The FDB is an object store which allows to store, index, and retrieve data to make them available to external users. It's the underpinning infrastructure of the data lake. Multi-IO is both an IO server for distributed Earth system model, as well as a new temporal and spatial post-processing capability. Polytope will allow to extract very efficiently data along all dimensions, and think, for instance, of a user who would like to extract information along a navigation route. So Polytope will make it more efficient. Plume is this plugging API which will allow impact sector models to be plugged directly within the IFS to extract high-frequency information. And Aviso is a software to send notifications upon task completions to really bring all those workflows together, and also to notify users that some tasks are finished. So if we want to mitigate climate change impacts, we need a combination of both short-term response strategies and long-term adaptation measures. And I want to illustrate that with one single impact sector, wind energy. At short term, you would like to know how to protect the equipment and to know what will happen with energy production when extreme weather is rapidly developing. But on long term, you would also like to know how much energy we can expect to produce, considering that the large-scale circulation of the atmosphere is changing, and where to build the next generation of wind farms. So we need two digital twins for weather and climate adaptation, but underpinning those two DTs, we have a seamless system working across timescales and a common framework. So let's dive a bit more into detail about those two digital twins. First, the extremes DT, the weather DT, is made of two components. First, the global component, which will monitor every day under the global scale extreme weathers systems and 4 days ahead. And it will use for that IFS NEMO forecast at 4.4 kilometer resolution. It's developed at ECMWF. And upon the detection of some extreme event, it can trigger and configure a regional component which will run at 750 to 500 meter resolution. And it can be one of the three models, AROM, Harmonia Rome, and Alaho. And it's developed by a large consortium led by Météo France. Further downstream, we have impact sector models which will provide information to users about weather impacts. And for instance, to illustrate that, if the Medicaid Llanos was to be simulated by the global DT, it would trigger several regional domains along the tracks, and further downstream, the users would be able to retrieve information about river discharge from one of the 9 hydrological models that have been already implemented in the regional component, or from the hydrological model EHYPE, which is a European-wide model also integrated in the regional component. We have, since August last year, run this extreme DT every day, and with the support of the teams at ECMWF in charge of the evaluation of the operational forecast, we analyzed a number of events, including tropical cyclones, windstorms, and heavy rain events. We have compared them also with the new AI models to see where the kilometer scale might be adding value. And many of those cases, those which are underlined, are being also simulated with the on-demand regional component to see where the sub-kilometer scale is also adding value. Another DT is the climate DT, and it's the first attempt to operationalize climate projections. It can be, so we are running 3 global models at a resolution close to 5 kilometer, IFS NEMO, IFS FESOM, and ICON, and the development is led by CSC, and it's also a large consortium. One of the challenge is that those 3 models have different output formats. So we need to first find a solution to unify the format to have the same data with the same units on the same grid And for instance, we have decided to use a common grid in peaks, which have a very nice property to, for instance, compute coarsening of data very efficiently. Then we have the one-pass algorithm, which will allow to stream high-frequency data that would not be saved otherwise. The diagnostics that are produced can be visualized on the web platform Aqua. And further downstream, we have also integrated impact sector models, which can use directly either the generic state vector, which provide this unified format, or through the one-pass algorithm. Just to explain a bit more how this one-pass algorithm is working, it's a streaming algorithm which allows to reduce the amount of data that are produced by the DT to perform a computation by impact sectors on the fly. And here I take the example of wind energy, where the model is producing high-frequency outputs, and the one-pass algorithm is extracting 100 meter wind on the native grid, and at a model time step, we can extract information at a given location to process distribution of wind speed, but we can also compute climate indicators, just like the capacity factor, which will allow to give an idea of the efficiency of wind production over a given period without having to save very frequent outputs, which would take too much space on storage. One challenge of the climate DT is that those simulations are really expensive. The kilometer scale simulations are expensive, so we will not have a large ensemble to address the uncertainty in model response and in internal variability. So we are also producing storylines which investigate a specific scenario and which allow to reframe the question for risk mitigation under this given scenario. And in Destiny, we have explored one type of storyline where IFS FESM, which is a spectral model, is nudged toward era 5 for the large-scale circulation, and then can be forced by different relative forcings. And we can compare here how a heat wave in the present climate would be represented in a 2-degree warmer world. And you see the level of detail that we can achieve, and that would benefit impact sectors to decide about mitigation measures. An overview of the climate simulations produced by the climate DT. We have historical runs covering 30 years and initialized in 1990. We have also future projections under the SSP3 scenario, all the way to 5-kilometer resolution in the atmosphere. We have also control experiments which are running under a constant 1950 relative forcing. And we have the storylines which are driven by the large-scale circulation of the period 2018 to 2023, and exploring various relative forcings and in a +2-degree warmer world, or back to 1950. In the phase 2, we will make sure that we will harmonize the configurations which are running in present and in future. Here it was a demonstration of capability. And we'll also run more scenarios to really address best different mitigation strategies. Part of the simulations will be available from the 10th of June on the Destiny platform, and so we really encourage you to have a look at them. So what is the improvement due to kilometer scale? When you analyze those simulations, there are some immediate effect of increasing resolution. One of them is increasing orographic precipitation. On the left, I illustrate this with the case of the storm Alex in the extreme ZT, and you see how the operational forecast H-res at 9 km represented the precipitation along the Ligurian coast. I don't know if you see the arrow is here, and it was underestimated compared to radar and rain gauges observations. But when we increase resolution, we see how this orographic precipitation increased, in particular in the southeast of France, where most of the impacts were recorded. It's not just pure luck, because if we investigate 10 case studies of extreme orographic precipitation, we see that in a quantile plot, as we go towards higher resolution, we get closer to the line of slope 1, meaning that we increase the precipitation rates in better agreement with the observations. And if we look at a full season of daily forecast, we see also how we improve the representation of the largest precipitation rates. Obviously, there are challenges, and one of them is the double penalty issue. As we simulate very fine details, a slight mismatch in space and time can be highly penalized by the traditional metrics to evaluate NWP forecast, like RMSE. So we are also working on other metrics to evaluate precipitation, like the error allocation metric. Another thing that we improve is the representation of tropical cyclone. We see here a simulated satellite image in the visible, and you see how on the top left, the operational forecast misrepresented the rain bounds of the tropical cyclone and the eye that was we see in the satellite posed images. But when we increase resolution, those features are much better depicted, and they are essential to represent correctly the intensification of the tropical cyclone. That's actually one of the success story of Destiny and tropical cyclone Idalia, which occurred a few days after we launched the daily forecast with the global DT, was completely missed by the operational forecast in red, which did not even reach a category 1, but Destiny managed to reach category 3 in good agreement with the observations. Again, this is not luck, because when we analyze 2 seasons of Destiny forecast, we find that the pressure-wind relationship of the Destiny forecast in green is in much better agreement with the observations in black. Another thing that we have been working on is the representation of cities, and if we really want to exploit the kilometer scale information, we need a proper treatment of cities. So we have in the project NextGem, in the cycle 3 of the simulation, activated the urban tiles in the land surface scheme, and you see how we can depict very nicely now the urban heat island effect with very warm temperatures in the region of Paris and Brussels, and you see many more of those cities emerging at high resolution, showing that the treatment of cities is very important at kilometer scale, and those were completely missed in cycle 2, and we are now in much better agreement with the land analysis of LSA. If, for instance, you take the example of Brussels and you consider the anomaly of temperature with regard to the surrounding areas, in the cycle 3 in blue, you see that we are now in very good agreement with LSA, much better than was the IFS simulation of the cycle 2. In particular, you see how the thermal inertia means that the temperature remains very high at night, much warmer than during the early morning, and that was completely missed by the cycle 2 simulations. And that's very important for thermal comfort and for health issues. So we will bring to users here an information of better quality. So what did we need to work on? What did not work straight out of the box? NWP scores first. So we have produced the first scorecard of an NWP forecast at kilometer scale. And here on the left, you saw the difference between the 5 kilometer, the destiny forecast and the operational forecast. Blue means improvement and red means degradation. So we degraded a lot the scores in the destiny forecast, in particular in East Asia and over the Himalayas. So we have been working on filtering the mineralography, reducing the time step, and changing some limiters in the convection scheme, as well as introducing some degree of off-centering in the implicit semi-Lagrangian scheme. And we now arrive to the scorecard on the right, where things are improved. There is still work to do to reduce the scores, but those errors in scores, but we are really on the right track. So one way to achieve this reduction in score was better treatment of the mineralography. The IFS is a spectral model, and the mineralography is represented spectrally. But the IFS has also a difficulty to represent accurately small-scale gravity waves. So we need to introduce some degree of filtering of the small-scale mineralography. And you see on the left those different spectra of orography. The top curve is for various resolution, the orography without filtering. The intermediate curve is the current orography with some degree of filtering of the small scales. And in Destiny, we have explored more filtering, and we see on the right how the difference between forecast with more filtered mineralography and versus the current forecast, and we see how we reduce errors in 30 degrees north, that is to say over the Himalayas, and in particular around the tropopause. So we have reduced the gravity waves that tends to propagate too much vertically in hydrostatic model, and which interacts badly with the subtropical jets. But you see that this reduction of error is even more important at high resolution, at 4.4, than it is at 28 kilometers. So treating correctly the mineralography is really crucial when we reach the kilometer scale. Another question is, can we simply turn off the parametrization of convection? This is an important question because many of us in our community switch off the parametrization of deep convection. And on the right, you see how the cloudy brightness temperature is represented in the observations and the precipitation field in GPM. In the current scheme, we have deep convection on, and we have clouds which are too diffuse, and we have too much light rain and too diffuse rain as well. But if we simply turn off the parametrization of deep convection, we start having very popcorny anvil clouds and also precipitation rates which are too spotty and too high. So in the cycle 3 of the next year experiment, we have reduced the cloud-based mass flux, and we find that we have now a better representation of convective precipitation. And if now you move to the left, you see how the next-gen simulation in red is in better agreement with the observations in black in terms of precipitation rate. However, we are still underestimating the number of mesoscale convective. Sorry, we are still underestimating the size of the mesoscale convective systems. So we are also working on introducing Lennard term in the IFS, which we hope will bring more mixing and broaden the convective updrafts to extend the size of mesoscale convective systems. This is good progress, and this is what we use now in the climate DT. However, this reduction of the cloud-based mass flux is degrading NWP scores, and we cannot use it in the extreme CT, but we are really working hard now to compensate the degradation of scores that it causes. Another success story, and which shows how the development of the weather and the climate DT can benefit each other seamlessly, is the tuning of the global kilometer scale model. We know that in the IFS, we are not conserving moist species because of the semi-convention scheme, but it was thought to be a minor issue for the operational forecast due to the short time range that we explore. And but in the climate simulations, it was shown to cause a major drift, and so the water budget, which was not closed, was fixed by introducing a mass fixer for most species, and this closure of the water budget also was beneficial for the energy budget, and the TOE imbalance moved from 6 watt per square meter to something close to less than 1 watt per square meter. And this improvement for the climate DT was also beneficial for operational forecast at ECMWF, so that it was decided to activate the tracer mass fixer in all operational forecasts. And in particular, we saw that we reduce a lot the temperature error in this scorecard in the tropics. So we're still working on a number of topics. In particular, the question we are often asked is the hydrostatic assumption still valid at kilometer scale? The hydrostatic assumption matters for the representation of gravity wave drag. You see on the bottom left, there are 2 regions where we generate gravity wave drag. It's in the deep tropics, in regions of the ATCZ in red, and along the subtropical jet. And when the waves propagate towards the stratosphere, and when they break, they can influence the large-scale circulation. We can now compare hydrostatic and non-hydrostatic dynamical core using the same numerics, and we show the difference of hydrostatic and non-hydrostatic on the right. And you see that there is only one region where it really makes a difference. It's in the Himalayas, and under very specific circulation when the subtropical jet is very strong. So there was no changes in regions of deep convection. So it's kind of good news. It can mean that we can get sorted by filtering more the mineralography. And it's good news because the non-hydrostatic dynamical core is 2 times more expensive than the hydrostatic dynamical core. And we can consider continue using the hydrostatic assumption for the time being. We are also working on subgrid orographic processes, and on the left here, the representation of the various subgrid drag, and on the right here, their contribution to the total angular momentum budget of the atmosphere at various resolutions. The subgrid orographic drag, and the flow blocking are depicted in orange, and you see how their contribution reduces at when we increase resolution, and as the resolved drag is increasing, and the turbulent orographic form drag and turbulent dragging are represented in green, and their contribution are much flatter across resolution. But we have really worked on the way we process the orography fields so that they evolve more smoothly across resolution. We have also tried to exploit higher resolution data, 30-meter data from the Copernicus STEM dataset to have a better depiction of subgrid orography fields. And we are also using a new approach for tuning the subgrid drag, which is a Bayesian optimization strategy, which will allow to get more rapidly to the solution, to the optimal solution. I'm checking how I'm doing with time. We'll try to wrap it up. So a success story of Destiny was the simulation of the tropical cyclone Otis, which made landfall in Acapulco last October. And it was a major forecast bust because no NWP model managed to predict its intensity. And we have shown in Destiny that by combining a number of developments, by using extra observations, by, in addition, reducing the cloud-based mass flux, and also by moving towards higher resolution 4D VAR, increasing both the resolution of the background trajectory and the minimization of the 4D VAR, that we could move that we could simulate a tropical cyclone of category 5 when the original Destiny forecast did not manage to reach even category 1. So we know that it's the way forward, but the high resolution for DVAR is extremely expensive, so we cannot really afford to run it now. And as I said before, the reduced cloud-based mass flux is degrading scores in the tropics. But we are working really hard on improving those scores. We have been working on quantifying uncertainty with physics-driven models, and we have evaluated for the first time our uncertainty quantification scheme, SPP, at kilometer scale. The conclusions are, in terms of the added value of the kilometer scale, are the same as in the deterministic forecast. So you have the extreme precipitation associated to a medicaine on the top line, and you see that the precipitation are increased in the region of Pilion at 4.4 kilometer, but there are even more when we use the reduced cloud-based mass flux and proper initial conditions. Similarly, we see that we increase the intensity of the tropical cyclone Otis at 4.4 kilometer. But if we want really to leverage the added value of the kilometer scale, we also need to use the proper physics and proper initial conditions as depicted on the bottom right panel. We are working on a new turbulence scheme. The current scheme is a first order closure scheme. And as we are moving towards high resolution, we want a more dynamical representation of turbulent processes. So we are introducing a prognostic TK scheme. You see how for a fog case in Northern Europe, the current scheme predicted the right cloud cover at a lead time of 53 hours, but as we increased the lead time, the cloud cover was not very well represented. And when we move to the new scheme, even at long lead time, we can now simulate correctly the cloud cover. And it's because the TK scheme is much better at representing the transition between regime and to move towards a stable boundary layer regime. We also hope to improve the representation of the diurnal cycle of the boundary layer with the TK scheme. We have integrated successfully impact sector models in the global DT, and one for floods with the river routing model Kana flood. So we really hope here that the river routing model will benefit from a better definition of river catchments and of orographic precipitation when we move towards high resolution. We have also integrated flexible aerosol, prognostic aerosol scheme for air quality, and it builds on the scheme used in CAMS, but the development allows to select some aerosol species that are treated prognostically while keeping all the others climatological. And the motivation to include those impact sector models in the global DT is not only to bring to users the information they need, but also because they might feedback on the large scale. Think, for instance, of the impact of dust on radiation. And so we also hope to improve our Earth system model by integrating and coupling those impact sector models to the rest of the model. So to conclude, how can we engage in Destiny with the lighthouse activity on digital health? I think we have a unique position because we are developing seamlessly a weather and a climate digital twin, meaning that we can assess very accurately NWP forecasts with all the tools that we already have at ECNWF, and we can inform the development of climate models. We hope to feedback also our experience in co-designing the digital twins together with users and let the lighthouse activity know about their specific requirements. We will provide an open access to the data of the digital twin, and you can already test the beta version of the Destiny platform until the 17th of May, and then again the final version on the 10th of June. And if you want to retrieve digital twin data, you can use the Insula service. The softwares of the digital twin engine are open source, and you are also welcome to use them. And what we would benefit from, we would really benefit from a joint investigation on the best physics for kilometer scale. And I know that some activities have already been initiated, for instance, on the linear terms that I mentioned earlier, but there are many other aspects that would also benefit from having dedicated groups working together. We would like to hear about new observation data sets to evaluate the kilometer scale. We will benefit from your expertise in analyzing the digital twin data. And finally, a crucial question that has been addressed already a few times in the seminar series is the role of the kilometer scale on the large scale circulation. And we are really looking for evidence of that. As you see from scorecards, it's possible that this upscale effect is still masked by model errors emerging at kilometer scale. But yeah, we would really be interested in working with you on that. To conclude, I would like to thank all those who have contributed to this presentation, or whose work has contributed to this presentation in Destiny. And I would like to thank you for your attention.
Thank you so much, Benoit, for a fantastic talk, and congratulations to you and all of the team's work that this represents. We have just under 10 minutes to try and work through some questions that we're going to pick up from the Q&A. So if you want to your question from the chat reflected in the discussion, then please raise that in the Q&A and we'll work our way through. So Rosie, do you want to kick off?
Sure. I believe the first question was related to one of your earlier slides. It's coming from Sarah Gamon, and she's asking, is there any filtering between the two different scales in order to unify the outputs, or are they presented as is with potential deltas between the two?
So, sorry, unifying the outputs of the weather and climate. Oh.
I believe that was referring to that, yes.
So the data portfolio of Destiny are largely the same, and yeah, so I think you can investigate the same fields in the two digital twins. Yeah.
I think we've had a number of people very excited to get hold of the data, and you've addressed that maybe in the last comment. So we'll maybe move on to a question from Ashish Mitra, who says, great development work. And for the 5 kilometre global model, how is the model mean climate and its interannual variability in different climate zones? So how representative in particular is the South Asian monsoon variability? Can you comment on that, please?
No, I cannot comment. You know, as I showed on the slide, the simulations are still running for some of them, and we are really now trying to evaluate their quality. That will be really a focus of the phase 2, and for that we also hope to get feedbacks from you. So I cannot really comment on the representation of the monsoon in the climate simulations for now.
Okay, thank you. We have another question here. What are the actual improvements in urban tiles representations? For example, Brussels case.
So what is what is the improvement? Or
in urban tiles representation? I believe this was referring to the slides on the urban.
Yeah. So I'm not an expert of the detail of the representation of urban tile. What I can say is that at least we have a specific treatment. I think it's relatively basic for now, and that will be improved. And in particular, all buildings have the same height, and so it can be complexified. And there is only one layer really which represents the thermal capacity. So yeah, more development will surely come in future.
I think there's been some debate in the chat as well about a question from Mujtaba Hassan, and he asks in particular to elaborate in more detail about why you cannot just turn off the convection parametrization at these scales, and particularly relating to your non-hydrostatic model. Are there any references for that? And maybe a supplementary question on that is, do you think that will still apply when you're down at like 1 kilometre scale?
Why can we not turn it off? As you see, when it's off, we tend to simulate too strong precipitation rates that's in yellow compared to the observations. So the convection is too intense. Probably it's generated or triggered when K is really high, and I think I can say, and you can confirm that the Met Office has reached similar conclusions, that keeping some degree of parametrization of the convection is better than turning it off completely. So I think we are converging with other groups on this conclusion. Whether it will remain true at kilometer scale, I think that we have investigated, and we see really how deep off and deep on are converging when we reach a kilometer scale, because the flow, the convection is now explicitly simulated, and so yeah, the degree of activity of the convection scheme is reduced.
Okay, and for the next question, this is coming from Dr. Partha from Pune, India, and they're asking that a number of models, including Destiny, doesn't seem to be capturing the location of extreme precipitation very correctly. Has been observed in the current backdrop of climate change. Capturing the location, time, and magnitude of extreme is crucial, which doesn't quite come in any of these initiatives. What's your opinion on this and how to get it right?
So not being able to pick the right location for extreme precipitation. I'm not sure what the question is referring to more specifically, but I think there are certainly improvements to be made, and the location of deep convection is also enslaved with the large scale circulation, which depends on many other factors. So what we really want to improve for now is those statistics and having precipitation rates better aligned with the observations, and yeah. So I'm not sure I'm answering the question, but that was a challenging one.
We'll maybe leave it at the challenging question, and unfortunately we haven't had time to get through everything, but Benoit, if you will capture the questions that have come in and for your consideration, and I'm sure Benoit would be happy to hear from people more directly after the event, and another plug for the launch event on the 10th of June as well to hear more. So just before we wrap up, to highlight that any feedback on today's event is very welcome, and you can send that directly to myself or to Rosie, and we can share contact details. I'll try and get them up on this slide just now. So feedback welcome at any time. And we're also very happy to hear from anybody who wishes to volunteer a future talk or has particular topics or themes that you would like for us to address in future events. And we're just lining up speakers through for the rest of this year at the moment. And hopefully this series will continue to offer a chance for people to advertise their work and for this kind of dialogue. And thanks again, Benoit, for today.
Thanks a lot.
Next time, we're looking forward to a presentation by M.N. Raghavendra Srivastava and colleagues from the National Center for Medium Range Weather Forecasting in India, who will be talking about convective scale global modeling for the Indian monsoon.
And so just, Rosie, over to you. Just to say then, we will let you know when the recording for today's event is available and open up registration again for the next event. And thank you all for your participation and for attending today's event. And a final thank you to you, Benoit, again, and all your colleagues for some great work shared. Thank you all.